Morning, everyone. Can you guys confirm if you guys are hearing me?
Yeah.
Okay, I want to welcome everyone to my lecture today. Today, October 30, 2020. I'm actually going to be uh, discussing another important concept in statistics. And I think I'm actually going to start from where we stopped on Wednesday. Though I've the material today will be I actually extracted that from where we stop from the material for Monday. I mean for the material for Wednesday. Okay, so I need you to actually pay attention because we got a lot to do today. So this is a continuation of what we did on Wednesday, and that was why I call that analysis of variance part two. Okay. Okay. So, like I said, I'm actually gonna move to the next slide right now. Now, in the outline for today, I'm actually gonna start from checking ANOVA assumptions. Then from there, I'm gonna briefly describe the concept of least significant difference that I call LSD. And after that, I'm actually going to walk you through what we call regression approach to ANOVA. Now, of course, you remember the other time that I we're using one example that has to do with a branch of tiles. Of course, I've walked you through how you can do that in R, and we actually took a decision, okay? And the decision we took was that okay, the p-value was less than the given level of significance, and the non hypothesis was actually rejected. And after that, we actually conducted a Turkey HSD test, which I called, you know, in order to figure out where the different lies. Okay, we are called a multiple comparison that was done, and the next thing that we're supposed to do after that is to check whether absorption on the line, the use of ANOVA are satisfied or not. And that is where we want to start today. You don't just take a decision using the model without investigating whether uh, you know, assumptions are met. And that is I'm actually going to call that, you know, uh, diagnostic checking. Now, you remember the other time that you run an analysis and we actually uh, use, well, we call it, the code was model one. Now, if you plot, take a look at what I'm trying to, if you take a look at this guy now, this is the code, okay? I actually want to generate 2 by 2 plots. This one per info means because I want a 4 plot. There's a 4 plots, okay, that I need. And that was why I indicated per info, 2 by 2. Then I'm actually going to plot. Okay, when I plot right now, you're actually going to see. So when I plot, take a look at that. You are seeing a 4 plot, residual plot, the normal KQ plot, the standardized residual plot, and the one for the constant leverage. Take a look at these 4. These are the 4 plots that we actually need, to be able to investigate whether assumptions in the analysis of variance hold or not. And if we're actually going to look at this plot one by one. Each plot we actually address a particular absorption. Don't Let me remind you, there's what we call um, normality assumption. There's what we call independence assumption. There's what we call the assumptions of constant variance and so on like that. Okay. Now, if you take a look at the residual plot right now, if you take a look at this guy here, what this guy is actually telling us now, there is no pattern. Okay. And which means the variable, the predictor variable that we considered in this analysis of variance, we actually do a good job. There is no any other additional predictor variable that will give us good information about the mileage that we actually want to talk about. Okay, so because of the fact that there's no pattern here, and that actually indicates, that the predictor variable actually did a good job. Now I'm going to go to this guy here. This is a normal QQ plot. The normal QQ plot actually it's testing whether there's a violation of assumption of normality. Okay, but when you take a look at the normal QQ plot, you're going to see that majority of the points actually fall on the diagonal straight line. And when you look at that, then that is giving an indication that the normality assumption hold. Okay. Now, the next one now is we want to talk about this guy here. And of course, that guy there, the studentized residual actually agree with the first plot. Okay. And take a look at this guy here, the one for the constant leverage, the constant variance. Then you're actually going to say from one brand to the other, of course, they have the same amount of variation. Take a look at that. Okay, and that was the reason why I actually put I put interpretation right here. Take a look at that, so you can read the interpretation. So I think the four graphs, the four diagnostic plots actually confirm the fact that the assumptions are not violated. Okay, but let me tell you this: we cannot rely on graphical means. We can't rely on this. Therefore, we also have a standard way to check for these assumptions. Because the reason why we cannot rely on this is because different people may have a different way to interpret a graph. And that is the reason why we're actually going to have a standard statistical way to investigate violations. Okay? Now I'm going to show you that right now. I'm going to start from here. The other time, if you look at the first plot, was talking about the behavioral pattern of the residual. Okay, and take a look at this. If I want to have a statistical, if I want to have a standard statistical test, then I'm actually going to have a test. Look at the hypothesis. Okay, the hypothesis here is that look at the non-hypothesis is going to say the sample observation are taken from a normal population. Again, the sample observations are taken from non-normal population. And you know what? In my model that I've specified, that I've run in R, if I want to get that, look at the code. I'm actually going to write recede. Recede is for a, is a symbolic code for residual in R. So I'm going to write recede my model. And when I write receipt my model, take a look at that, the receipt my model. After that, then I'm going to do Shapiro.test. There's somebody that we call Shapiro Wiki. The Shapiro Wiki test of normality. If you want to test whether normality assumption hold, we're gonna conduct what we call a Shapiro Wiki test of normality. So the Shapiro.test of U hat. Now, look at the U hat. The U hat is what? The receipt of the model, right? Now, the Shapiro Wiki test of residual now is actually going to give you this guy here. Take a look at that. The Shapiro Wiki test is a standard statistical test to test for normality. If you want to test for normality, okay, you're going to use Shapiro Wiki test. And we're going to focus on the p-value right here. Take a look at the p-value. Now, the p-value right here is actually greater than 0.05 level of significance. Therefore, we're going to fail to reject the non-hypothesis. Now, the question now is, what is the non-hypothesis? The non-hypothesis is that the sample observation are taken from normal population. Therefore, the normality assumption hold because we fail to reject the non-hypothesis. Because the assumptions of the ANOVA is that the samples or observation should actually come from normal population. But in a situation whereby you reject the non-hypothesis, that's a violation. Okay, that's going to be a violation of normality. But right now, there is no violation of normality. So which means the Shapiro-Wilkie test of normality actually agree with the plot, actually agree with the normal QQ plot right here. Take a look at that. They agree. Look at that. So the normal QQ plot is just the graphical tool to investigate normality. But you know what? The standard statistical procedure to investigate normality is Shapiro-Wilkie test of normality. Okay, so that is how the test actually work. Very simple code. You're gonna get your result. Is there anyone who want to ask question before I move to next investigating next assumption? Is there anyone who want to ask question? Are you guys still hearing me clearly? Okay. Now I'm actually gonna move to the next one right now. And of course, that is interpretation. Of course, that implies the samples are taken from normal population because the p-value is higher than the level of significance specified. Now, the next assumption that I want to test is the assumption of the homogeneity of variance. Homogeneity of variance means we have a constant variance across the group, and that is required. And if I want to test that, then I'm going to use what we call Bartlett test or Levene test. There are different kind of, tests to test of homogeneity of variance. And you know what? If you want to carry out the test, we're actually going to state the non and the alternative hypothesis. What is going to be your non-hypothesis? Your non-hypothesis is going to talking about, we're going to be saying that there's constant variance across the group. And the alternative is actually going to say there's no constant variance across the group. Okay? Now, the test of homogeneity of variance, homogeneity means equal variances. And let me tell you, in another way, your non-hypothesis will be we can also call that homoscedasticity. Why the alternative will be heteroscedasticity. That's another word. The homoscedasticity is talking about constant variance. Heteroscedasticity is talking about non constant variance. Okay. Now, after having know that, then how are we going to run the test now? Oh my God, this is a code. If I want to do a Bartlett test, I'm actually going to do Bartlett.test into mileage on brand. Don't forget, we are actually, the predictor variable was brands, and the response was mileage. You remember that? And at the end of the day, take a look at what I have. This is the result that's actually going to come out from that. The simple code in R will give us this result. Now, let us now examine, take a look at the p-value. The p-value here is greater than, a level of significance given. If a given is 0.05 right here, of course, the p-value is greater than that. And when p-value is greater than a specified level of significance, then we're actually going to fail to reject the non-hypothesis. And what is the non-hypothesis? The non-hypothesis is actually talking about equal variances. And that is what is required in the analysis of variance. Now, the p-value we obtain here is greater than a level of significance given. Then because of that, we're actually going to conclude that there is constant variances among the groups. So which means there is no violation. Okay, there's no violation. Is there anyone who want to ask question before I move on? Is there anyone?
Um,
Okay,
for
go
the
ahead.
test for variances, so is it um if like this does it every group have to be the same like sample size or for it to
Oh,
work, or is it doesn't?
okay. You mean did you say every group have to have the same variance? Is that what you mean?
Uh, or yeah.
Yeah, what the constant variance is talking about is that even though the sample variances may not be the same, but population variances will be the same. There's a difference between the sample variances and population variances. So the assumption here in analysis of variance is that population variances should be the same across groups. The if I'm talking about 4 brands of tires, then they should all have the same population variances. The population is just that you are considering everything in this world. You are considering all brands of tires, which is not possible. And at the end of the day, what you're going to do is just to take a sample, right? But the assumption is that before taking a sample, assumption is that population variances have to be the same. And that is just an assumption. And you are right. So population variances have to be the same. And you know what? Since it is an assumption, that need to be tested. And that is what we actually tested using the Bartlett test. So the Bartlett test will tell us whether that assumption hold or not. If that assumption do not hold, if the p-value is less than level of significance, it means that assumption do not hold. Then it means we cannot continue. We cannot rely on the decision we have taken before. Something needs to be done. Does that make sense to you now? Okay. Now, I'm actually gonna. So that is that on the, you know, the I was checking for assumption. I check for the assumptions of normality, and I also check for the assumptions of constant variance. Now, the next thing that I'm going now, the other time I actually discussed the multiple, uh, uh, um, what is it called? I talk about multiple comparison, and I gave you an example. For multiple comparison, there are different kind of tests. There are different kind of multiple comparison tests. But the one we use on Wednesday is Turkey HSD test. There are other tests that can also be used, and that is what I want to discuss today. I want to discuss what I call the least significant difference test. Okay, we use that in multiple comparison in situation whereby the non-hypothesis has been rejected in the analysis of variance. Now, because of that, I want us to use a different example now. Now, take a look at the question right here. Does number of good friends depend on happiness? Now, we want to answer that question. You know, um, it is the fact remain that we need friends. Okay, and it is scientifically proven that you know when we have friends, friends make us make us happier. Okay, but the fact remain, the nature of happiness actually depends on our personality and the nature of friendship. Okay, now the question now remain: how happier are we actually going to be if we have a good number of friends? Some of us, we have friends on Facebook, we got a good number of friends on Instagram, and we also have some numbers of close friends. But let me tell you, A researcher of recent conducted, you know, a research and realized that if you have the minimum of 3 to 5 close friends, yeah, from a study, I think the name of that person was, let me remember, White. So White actually concluded that, people that have 3 to 5 close friends reported the highest level of life satisfaction. Okay, and if we now want to investigate using the knowledge of analysis of variance, well, we want to know how much happy are we actually going to be if we have a good number of friends. And that is the reason why the general, survey study conducted a research, and this is the result of the research, where we consider, are you going to be very happy, or you're going to be pretty happy, or you are not going to be happy at all. Of course, how many categories do we have? We got 3 groups, okay? And we got, this is the mean, for the 3 groups, the sample mean of the 3 groups. This is the sample standard deviation. And of course, the number of people that reported very happy, they are 276. The number of, respondents that reported pretty happy is 468. And the number of, a respondent that reported not too happy at all is 87. Let me tell you this, it's good to have friends, but there are some friends that will be happy when you are, they will be happy when you are happy. In fact, they will be more happy when you are happy. And there are some friends that would like to pull you down. And that is the reason why we need to be careful with friends, where it is not going to be just quantity, but quality. Okay? Not just having friends, but you need to have a quality friends. Now, take a look at this example right now. What the analysis of variance want to do here is to be able to compare the means of these 3 groups. We have seen the mean 10.4 for very happy, 7.4 for pretty happy, and not too happy 8.3. Now, take a look at this guy here. And the very first thing we're going to check, of course, we're going to check whether they are from normal population. You know, we check, I just walk you through how to check for absorption, because that is one of the assumptions of analysis of variance. Do you think the population distributions are normal? Okay. Then if let me tell you something. When you carry out, when you investigate normality absorption, and if that absorption is violated, then it means we cannot use analysis of variance anymore. Then we got to use something else, which we are still going to do. We call that Kruskal-Wallis test. Okay? Kruskal-Wallis test will replace analysis of variance test in a situation whereby normality absorption is violated. I'm actually going to walk you through that in a subsequent lecture. But right now, we are assuming that normality assumptions are not violated. Okay, now, after carrying out this particular test, we have a result. What I have here is more or less like an output. Okay, now let us focus on the p-value. Look at the p-value. What do you see in the p-value? At a 0.05 level of significance, the p-value is less than 0.05. So which means we're actually going to reject the non-hypothesis. What is the non-hypothesis? The non-hypothesis is just that the nature of happiness will be the same. What is the nature of happiness? Here, the nature of happiness was categorized into 3. Into very happy, pretty happy, and not happy at all. Okay? That's going to be the non-hypothesis. The non-hypothesis is telling you they are all going to be the same. But the alternative hypothesis is going to say they are not going to be the same. And based on the p-value that I have right now, the p-value is less than 0.05. Okay? Of course, your decision is going to be to reject the non hypothesis. Now, after rejecting the non hypothesis, do you know that you may want to conduct multiple comparison tests to be able to know where the difference lies? Okay, you remember we did that on Wednesday, but on Wednesday we actually use Turkey HSD test. But today I want us to use an alternative test to Turkey, which I call the LSD. The LSD means the least significant difference. Now, take a look at this. That is the formula for LSD. Take a look at that because we're actually going to be comparing. We're going to be comparing, uh, the pairs of the mean. We got three groups right now, right? How many pairwise comparison are we going to have? Of course, I give you a formula. The formula is going to be G into G minus 1 divided by 2. What is G? The number of groups I have is 3. Okay, if you plug in 3 into that, it's going to be 3 into 3 minus 1 divided by 2. And that is going to be 3 times 2 divided by 2. Of course, the number of pairwise comparison I'm actually going to have is going to be 3. Okay, and if it is 3 pairwise comparison, of course, using the LSD, this is the formula that I'm actually going to use for the LSD. Okay, now if you take a look at if you take a look at this guy, this is just the difference between the pairs of the means. If you take a look at this guy, Ni and Nj is going to be the number from each group, the two groups that I'm actually comparing. And if you take a look at X is actually the square root of the mean square error. Where are you going to get the mean square error? The mean square error from the ANOVA table. I'm going to take you back. Take a look at the ANOVA table right now. The 234 here is the mean square error, the one that corresponds to the within groups. That is a mean square error. The square root of mean square error is S. Okay, I want you to take note of that. I'm going to do the square root of 234. 234 is a mean square error. Okay, if I want to conduct a least significant difference, my X right here, take a look. That was why I said this. Take a look at that. Okay, that is the square root of the mean square error, and the mean square error you compute in the ANOVA table. And of course, you cannot investigate, you cannot find a multiple comparison if you have not conducted the ANOVA table. ANOVA table will have to come first, and you have to take a decision of rejecting the non-hypothesis before you're going to proceed to the multiple comparison. Okay, now there's something I want you to see. The multiple comparison actually work in interval. Take a look at this. This is actually you're going to compute the interval, the mean of the interval of the difference between the mean between the pairs of the mean. Okay, and because of that, this guy here, the whole of give me 1 second. The whole of this guy here will be called margin of error. Okay, the whole of that will be called margin of error. Okay, the whole of that will be called margin of error. And you know what? This guy here is point point estimate of the difference. Point estimate of the difference between the pairs that you are investigating. Okay. Now, and don't forget, in the interval estimation, we are actually going to have the point estimate plus or minus the margin of error. Okay, and the margin of error will be subtracted from that, and the margin of error will be added to that. Then as a result of that, we're actually going to have the lower bound and the upper bound, and we're actually going to say the different the true difference actually lies in that interval. Okay, now if you're going to see if you take a look at just this guy here with the X.
Professor,
Okay, go ahead.
I have a question about the mean of I and the mean of J group. So do you have to like take the absolute value of that or like put whatever greater value? Because like if one mean is less or greater than the other, that would change the difference, right?
Oh, that is a very good question. If I hear you very well, or what you are trying, give me 1 second. I think this is, can you guys hear my voice very well?
Yeah.
Okay. Now, if I hear you clearly, you are trying to talk about this guy here, whether we're going to find the absolute value of that or not, because at times there's some difference that could be negative. Is that what you mean?
Yep.
Okay, that's a very nice question. You don't need to find the absolute value because uh, when the difference is negative, then it means one is greater than the other. Okay, so you are not going to find the absolute value for that when you are dealing with a confidence interval. Okay, but there are situations where you're going to find the absolute value that I'm going to tell you. But right now that we're constructing the confidence interval of the difference, you don't take the absolute value. Does that make sense to you now?
Yeah, I see. Thank you.
Okay. Now, uh, because of that, when you plug in the values of what we've done, you're actually going to see that is what. Look at that. This is the first pair, and the first pair. Take a look at this guy here. The first pair. Look at the interval. The interval is between the negative and positive value. And let me tell you this. When interval is between a negative and a positive value, it means a zero is included in that interval. And if a zero is included in an interval, it means there is no significant difference between the pairs compared. Are you guys hearing me? Are
Yep.
you guys hearing me?
Yep.
Okay, now what I just said right now, if you take a look at the interval that I cycle right here on the first pair, is the interval is between negative and positive value. So, and which means zero lies in that interval. And where zero lies in the interval, then we are trying to say there's no significant difference. Now, what do we just compare right now? We compare, the confidence interval for the difference between the population mean number of close friends for those who are very happy and not too happy. Okay? So, which means there's no difference between that. Okay? Now, another pair. This is going to be another interval. This is another interval. Don't forget, you're actually going to have three groups. Okay? You're actually going to have three groups. Now, if you take a look at this guy here, it's going to give you negative. There's going to be negative because it's 0.9 minus 3.5. That's going to be a negative value. Of course, the zero is going to lie, which means there is no difference here. But where does the difference lies? The difference actually lies here. Very happy and pretty happy. Okay, that is where the difference lies. Why? Because 3 3 minus 2.3 will not be a negative, will not give you a negative value. And of course, 3 plus 2.3 will not be. So it means the interval for that will not include zero. And where interval don't include zero, then that is where the difference lies. Okay? Where interval don't include zero, that is where the difference lies. Okay? I think you get it now. Okay, so now that is what I just explained right now is when you want to talk about the use of interval, the use of confidence interval, in multiple comparison. But if you don't want to consider interval and you only want to talk about the least significant different tests, this is going to be the formula. Now, the person that has a question the other time, this is where you're now going to talk about the absolute value of the difference. Like I said, we have two ways to look at that. We just look at the confidence interval approach of the least significant difference. But right now, we're looking at, the least significant difference proper. We're not talking about confidence interval right now. And what you're actually going to do, you're going to find the absolute value of the pair, of the difference between the pair, okay, of the means that you are considering. Now, situation, take a look at the formula right here. If you take a look at this guy here, this is assuming when the sample size of the first group and the second group are the same. But in a situation where the sample size are not the same, of course, what you're actually going to have is actually going to be this guy here, where you're going to have 1 over n1, and that guy is going to be 1 over n2. Okay? Now, the only condition for you to reject the non-hypothesis is when the difference between the absolute value of the difference between any of the pair is greater than this guy here. That is a condition to reject the non-hypothesis. And what is the non-hypothesis? The non-hypothesis is that the two pairs of the mean are the same. So when you are making use of this, approach, of course, when you have three groups, your 3 groups of comparison, you're actually going to consider 3 sets of hypotheses. Okay, you're actually going to consider 3 sets of hypotheses, and of course, the only way to reject is if the difference between the absolute value of the difference between that is greater than LSD. Okay, so that is that. Somebody said, what is the difference between this and ANOVA? ANOVA, like I said, ANOVA, before you come here at all, you have rejected the non-hypothesis in ANOVA. Don't forget, ANOVA has at least 3 groups. The limitation of ANOVA will not tell you where the difference lies. I'm going to say that again. Analysis of variance will not tell you where the difference lies, even if there's a difference. And that is the reason why we need multiple comparison. In the multiple comparison, you're going to know where the difference lies. But you know what? You don't go to multiple comparison until you have already conducted an ANOVA. And before you go to multiple comparison, the non-hypothesis has been rejected in ANOVA. Does that make sense to you now? The person that has the question? Okay. Now that is how to do that, okay? But let me tell you this. A lot of people will argue this with me. Why is it that instead of us to conduct ANOVA, why not just conducting a t-test on the peers? But the fact remains, when you do that, you actually, particularly when the number of group is large, when the number of groups to be compared is large, okay, then the type 1 error will be inflated. There's going to be a lot of error. You're going to take a wrong decision. And that is the reason why we have a way to correct that. Situation where we have group equal to 10, the number of group equal to 10, you're going to have 45 comparisons. 45 comparisons. Take a look at that. G, the formula is G into G minus 1 divided by 2. If you plug in 10, that would be 10 into 10 minus 1 divided by 2. 10 times 9 is 90. 90 divided by 2 is going to be 45. Then it means you're going to have 45 pairwise comparison. That is a lot. In a situation whereby the number of pairwise comparison is large, then there's going to be the type 1 error will be inflated. And how can we correct for that? How we can correct for that is this. If you want to construct a 95% confidence interval, and it means your alpha is going to be 0.05, then you need to, for force, divide your level of significance. You need to divide the number of comparison by the level of significance. Okay? Now, I'm going to say this again. You need to divide your level of significance by the number of comparisons. Okay? If you don't do that, you are actually going to record errors. Now, I'm going to show you right now. Take a look at this. You are considering 3 groups. Okay? And of course, considering three groups, you're going to have how many comparisons? That is going to be three, right? Now, you are no longer going to use a 0.05 again as a level of significance. If you're dealing with 95%, what are you going to do? You are going to divide your level of significance by the number of groups. If you don't do that, if you conduct a least significant difference for multiple comparison, then you actually, one of the interval you're going to have will not contain the true value. And that is the reason why what we're doing now is what we call bufferoni correction. Bufferoni correction. Where when the number of group is increasing, you need to divide the level of significance by the number of groups. And which means, look at this, the level of significance divided by the number of groups, that is going to be 3. Then this is what I'm actually going to be using now. Is 0.0167 is what I'm going to be using as my error rate. And that is what I'm going to use to get my t value that I'm actually going to use to construct my interval. Now, the other time when we conducted an interval, one of the interval is not correct. We know why? Because the interval, the only one that, take a look, I want you to take a look at this now. Take a look at this guy here and this guy here. The two of them will include 0. So which means the only difference that exists, is just for this guy here, just this guy here. That is the only difference, that is where the difference lies. But do you know that when we did that the other time, let me take you back. When we did that the other time, okay, this one includes 0. Take a look at that. When we did not correct, when we did not use Bufferoni correction, you know, take a look at this. This one includes 0. Now, this guy here includes 0. This guy here does not include 0. Anyway, there's an agreement here. Okay, there's an agreement because it's only one that does not include 0. And also here, it's only 1, 2 that does not include 0. Do you know the reason why they agree here is because the number of group is small. But I want to tell you, if the number of group is large, there is possibility that if you use the least significant difference of the confidence interval, one of the confidence interval will miss the true value, will not contain the true value. And that is the reason why when the number of group is large, it is recommended that you have to use Bufferoni correction. And what is a Bufferoni correction? You need to divide. You need to use the number of group to divide the level of confidence. I mean, the level of significance. And that's exactly what I just showcased. Now, somebody say, how large the group need to be considered? Oh my God, this is a very good question. Good job, good job. Now you are telling me how large is a large? That's what you're telling me now. Now, at least 3. You can see that when we make use of, when we use Bufferoni correction for 3 groups, and when we don't use Bufferoni correction for 3 groups, we take the same decision, right? So which means from 3 and above, that will be fine, okay? And some people will argue that with me that, okay, why can't you do from 4? Because Bufferoni correction, and without Bufferoni correction, you know, for 3 groups, you know, we have, let me just put it to you like this. At least the number of groups has to be 4. Let me put it as 4. Write it down. The number of groups have to be 4. How large? The optimal, you know, at least it should be 4. Because with 3 groups, we're taking the same decision. Now, today I'm actually going to be having just 5 minutes, additional 5 minutes, you know, because I want to explain. Now, let me quickly go to this. We want to have a regression approach to ANOVA instead of us to do ANOVA. Can't we have a regression approach to it? And the answer is yes. You know, in ANOVA, the response variable is quantitative and the predictor is categorical. Now, in a situation where you have three groups, that means three levels. Having three levels, that's a dummy. We can create a dummy. That's what we call dummy regression. The dummy regression is when we have dummy regression in situation uh, whereby we have dummy regression in situation whereby um, the predictor is categorical. Now, take a look at this. Situation where you have three groups, you're going to have two dummies. Okay? Three groups, three levels, the degree of freedom is going to be 2. Therefore, you're going to have Z1 equal to 1 if the observation is from group 1, 0 otherwise. Z2 equal to 1 is observation from group 2, 0 otherwise. Now, the regression model will now be this guy here. Take a look at that. Why do I have Z1 and Z2? I got Z1 and Z2 because I got three levels. I got three groups. Therefore, the degree of freedom for dumbing is actually going to be, I'm going to, if I have three groups, the number of dummy variable will be G minus 1. Take a look at that. So that is going to be 2. That's how I get Z1 and Z2. Now, for the mean of group 1, okay? Now, if I want to focus on group 1, what is going to happen? Now, focusing on group 1 means Z1 equal to 1. Focusing on group 1 means Z1 equal to 1, then Z2 will be equal to 0. When Z2 equal to 0, look at that. That guy is going to go away. Okay, I'm actually going to have alpha plus beta 1. Take a look at that. When I'm focusing on group 2, I'm going to do the same. Focusing on group 2, Z2 will be 1, Z1 will be 0. Therefore, that is the mean. Now, when I'm focusing on group 3, focusing on group 3 means I'm not focusing on group 1 and 2. Therefore, Z1 will be 0, Z2 will be 0. Then that is going to give me an intercept. Oh my God. So easy that way. Can you see how we construct the three groups right now? The mean of group 1, the mean of group 2, and the mean of group 3. Okay? By plugging in the value of Z1 and Z2. Now, well, what are the parameters in this regression? The beta 1, the beta 2, and the alpha. Now, what am I going to do? If I want to get a beta 1, take a look at that. If I want to get beta 1, okay, take a look at this. If you subtract equation 1 from equation 3, then that is going to be beta 1 will be equal to mu1 minus mu3. Take a look at that. Subtract, look at that. Subtract that. And at the same time, for beta 2, okay, if you subtract, take a look at this. That will give you, the beta 2 will be equal to mu2 minus mu3. Take a look at that. Okay, after getting that, this is what you're actually going to do. This is what we have done. Now, what is the prediction? The prediction here is just that I'm actually plugging in the mean. This guy represents the mean. The 8.3, the 2.1, the minus is 0, what you have right there, they are just the beta, sorry, they are just the alpha, the beta naught, the beta 1, and the beta 2. Now, there's something I want you to see right now. We have been given the mean of the group 1. You have the mean of the group 2. You have the mean of the group 3. Okay? Now, what I'm trying to tell you right now, the fitted model, when you regress Y on Z1 and Z2, you have done that already, where you have data under the Y, you have data under the Z1, you have data under the Z2. The estimate of the alpha and the beta 1 and the beta 2 is what you have here. And let me tell you this. When you plug in the values of Z1 and Z2, take a look at this. That will give you your mean for that group 1. If you want to get the mean for group 1, you're going to plug in Z1 equal to 1 and Z2 equal to 0. That will give you 10.4. If you want to find the mean of the group 2, then you're going to plug in Z1 to be 0 and Z2 to be 1. And if you want to find the mean of group 3, you're going to plug in Z1, Z2 to be 0, and that will give you this. So which means if we have run a linear regression, this is what we're going to get. Take a look at that. Now, if we get that right now, of course, you know what? I don't want to rush you. I'm gonna, you know, I'm going to add this. I'm going to start from here. I'm going to put this into the next lecture for Monday. I don't want to rush you. Okay. And of course, I only have just few pages. That's all. I'm supposed to start a two-way ANOVA on Monday, but I thought first start from there. I just have like 3 slides. I don't want to rush you. Is there anyone who want to ask question before I go today? Is there anyone?
Yeah, I had a question, but it was about practical assignment part 2. I just can't seem to find the assignment on the Canvas page.
You mean you don't find what on the Canvas page?
The practical assignment part 2.
Yeah, the practical assignment part 2 is just to import your data into the practical 2 port. That's all.
Oh, okay then.
I think I put the guide in the practical 1 when I said what you're going to do in practical 2 is just collect your data and import that into the practical 2 port. You are not going to do anything other than importing your data.
Oh, okay then. Thank you.
Does that make sense?
Yes.
Okay. Is there anyone who want to ask question again before I go today? Is there anyone? Okay. Like I said, I'm actually going to start from, ANOVA. Regression approach to ANOVA on Monday. I'm actually going to start from there. Okay. You're going to see the connection between using ANOVA or using the regression approach. I want to thank everyone who have attended my lecture today. And I hope you guys enjoy my lecture. Until on Monday again, give me 1 second. Why is this? It is mute. Can you guys confirm if you guys